Hello everyone, welcome to online video lecture series developed by Jawaharlal Nehru Technological University Kakinada in association with Andhra Pradesh State Council of Higher Education. This is Dr. M. Prem Kumar, working as professor in the Department of Electronics and Communication Engineering, Sri Vishnu Engineering College for Women, Bhimavaram. Welcome to video lecture series. Today's class we will discuss about lecture number 4, that is Convolution Integral. The previous lecture we have seen the convolution sum. Convolution sum is normally for discrete time LTA system. Discrete time LTA system, the convolution sum. Now same thing we will extend the same concept for continuous time LTA system. That is the convolution integral. So before getting to this convolution integral, let me represent x of t, any arbitrary signal in terms of its scaled and delayed impulses. So x of t can be represented in terms of scaled and delayed impulses. Integral minus infinity to plus infinity x of tau del of t minus tau d tau. So as we know that del of t is equal to 0 at t is not equal to 0 and its value is infinite at t equal to 0. And the area under this impulse delta of t integral minus infinity plus infinity delta of t dt is equal to 1. That means area under this impulse is equal to 1. So whenever you apply any arbitrary signal x of t LTA system, the corresponding output y of t is nothing but the transfer function of x of t. Okay. Now y of t is equal to transfer function of what is x of t? So integral minus infinity to plus infinity x of tau del of t minus tau d tau. Y of t is equal to, so we can take out this integration outside x of tau and this transformation del of t minus tau d tau. So transformation of del of t is represented with h of t. We know that whenever we apply impulse function as input, the corresponding response is impulse response. Because the system is a time invariant system, t minus tau, the same thing happens at the output y of t minus tau. Similarly, for positive shift, transformation of del of t plus tau is equal to h of t plus tau. So finally, this equation y of t will be equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau. This equation is called convolution integral. So y of t is equal to x of t convolution with h of t. This is an integral. Normally for continuous time LTI systems. Now x of t can be represented in terms of scaled and delayed impulses. By x of t, because delta function generation is not possible practically 0 at t equal to not equal to 0 and its value is infinite at t equal to 0. So for that what we will do is we will try to divide this into different intervals. This is delta. This value will be x of 0. Okay, height will be delta. Now what about this value? What about this value? That is x of 0 into delta. And coming to this value, this second one, this portion. This value is x of delta into delta of t minus delta. So in the previous case, this is thing into delta of t at t equal to 0. Now here, this will be delta. Delta. So this is with respect to the second pulse. Similarly, with respect to the third pulse, this value will be x of 2 delta and delta is shifted to 2 delta and width of the pulse will be delta. Now let me define this value delta of t, practically possible value. This value is 1 by delta at 0 less than or equal to t less than delta and its value is 0 otherwise. So now in order to reconstruct the original signal, that is f cap of t, this will be equal to, by adding all these values, summation x of k delta delta of t minus k delta into delta, and here this k will be from minus infinity to plus infinity, and keep adding all these pulses. These are all pulses. Now delta as this delta tends to 0, then delta of t value becomes infinite at t equal to 0. So this becomes ideal impulse function. So in this case, this summation becomes an integration. So in that case, x cap of t becomes my original signal x of t. Integration, summation becomes integration, and this becomes x of tau. This is del of t minus tau, d tau. But keep on adding all the small bits to get the continuous waveform. So this is how x of t represented in terms of scaled and delayed impulses to get back the original signal. This we can understand that x of t convolution with delta of t. As we know that y of t is equal to convolution between x of t and h of t. So delta of t is impulse function and h of t is the corresponding response, impulse response. So y of t is response of LTI system. This equation is called convolution integral. So y of t is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau will be equal to x of t convolution with h of t. This is convolution integral. Convolution integral. Now we will discuss about the properties of convolution. Of convolution, both in time and discrete time. First property is the commutative property. Commutative property, which indicates x of n convolution with h of n will be equal to h of n convolution with x of n. Both are same. Similarly, x of t convolution with h of t, h of t, which is equal to h of t convolution with h of t. So here both the cases to get the y of n. So here you convolution is commutative with respect of the input signal and impulse response. If you convolve two signals, you get the output y of t. And second property is the distributive property. So x of n convolution with h1 of n plus h2 of n. This will be equal to x of n convolution with h1 of n plus x of n convolution with h2 of n. Same thing in terms of continuous x of t convolution with h1 of t plus h2 of t will be equal to x of t convolution with h1 of t plus x of t convolution with of t. So this we can understand that interconnection of systems. This is one system and this is another system. This is h1 of t and this is h2 of t is common. So this is x of t. Take this adder, the output y of t. Here output is so x of t convolution with h1 of t. Here output is x of t convolution with h2 of t. So final output is x of t convolution with h1 of t plus x of t convolution with h2 of t. This is about distributive properties. And next third one is associative property. X of n convolution with h1 of n convolution with h2 of n can also be calculated by using convolution with x of n and h1 of n convolution with h2 of n. Similarly, in continuous time case, x of t convolution with of t convolution with h2 of t is equal to x of t convolution with h1 of t convolution with h2 of t. Let me represent in terms of systems. Of t. So we will have another system that is interconnected to this. This is nothing but y of t. This is h1 of t convolution with h2 of t. So you can combine. This is output y of t. Okay. Same thing, because convolution is commutative, we can interchange this h2 of t convolution with h1 of t. This is final output y of t, and this is input signal x. The same way, this is h2 of t and this is h1 of t, cascade connection between the system, and this is your final output y of t, and this is your x of t. And this is about associative property. The same set of equations holds good for discrete time case also. So this is h1 of n, this is h2 of n, final output is y of n. There is a connection between these two. So in here is x of n. So this is nothing but h1 of n, and this will be output y of n, and this is x of n. Because convolution is computed to h1 of n convolution with h2 of n will be equal to h2 of n convolution with h1 of n. h1 of n. Now output is y of n, and this is x of n. So similarly, this is h1 of, sorry, h2 of n, this is h1 of n, of n, and interchange these two systems. Final response is not changed. So this is your final output y of n. So convolution exhibits commutative property, distributive property, and associative property.